we're talking about solving non-homogeneous linear differential equations. And we're going to focus on, for today, where we also have constant coefficients. And so we have, our a sub n times the nth derivative of y, a sub n minus 1 times n minus first root of y, so forth and so on, all the way down to a0y equals f of x. So the non-homogeneous part means that there's some f of x on the other side, probably not 0. And we talked about this before, and we said, well, there's really kind of two big parts. The first part is we say, okay, suppose f of x were 0, and we solve for that. So in other words, stuff we can do. Because we know how to handle it. If we have this equal to 0, we turn it into an algebra problem, we find the roots, we read the roots, we set up what the solution looks like. Then the second part was, okay, find a particular solution, just one solution, where when we plug it in to the left-hand side for the function, we get f of x coming out. And then the last thing is really not much of a step. It just says, put the two together, and you're done. So we've talked about this before. Now, previously, when we said, okay, how do we handle the part where we have to find this particular solution y sub p? And the answer is, well, we want it given to us on a silver platter, saying, hey, here it is. And we're like, okay, great. And we verified it. Now, we're not going to have it given to us. We have to find it. That's our goal. That's our goal. So how do we do it? Well, we're going to split it into two big cases. And so think of it as the first case today, the second case next time. So today we're going to say, well, suppose f of x looks nice. Well, what do we mean by nice? Well, it looks like something that's the solution to some constant coefficient linear homogeneous differential equation. Not necessarily this constant coefficient linear homogeneous differential equation, but some constant coefficient linear differential equation. And we say, things that look like that, we can anticipate what the answer should look like. In other words, we can get the basic form of it, except we don't know what the right coefficients are. So we're very close to saying we know what the solution looks like up to figuring out what some coefficients are. And so we just have to figure out what the coefficients are, and we're done. So this is called the method of undetermined coefficients. And the idea is basically says, we more or less know what it looks like. We just have to sort of tweak and set the dials right. So what are things that f of x can look like? Well, things like powers of x, e to the 4x, x squared times e to something. So all of these are perfectly fine functions for things that are solutions. In fact, in general, we can say what our functions look like is x to some power e to alpha x, where k here is a whole number. I should emphasize that. Alpha can be any number. Sine beta x, or x to some power e to alpha x cosine beta x. And again, beta can be any number, alpha can be any number, but k is a whole number. Generally speaking, those are the types of functions that we like. Now, you might just have just the x to k, e to the alpha x, or maybe there's no e to the alpha x, it's just some combinations of sines and cosines. They may not even need to be x to a power. But those are the things that we have. So that's what we're going to talk about today. And then, everything else. Now, everything else says, okay, we kind of don't know what our answer looks like before we start. So we have to somehow form the answer. And we'll see how we can do that. And that'll be called variation of parameters. And that'll be next time. Now let's talk about some things that fit into everything else. So what are some examples of functions that fit down here? Do you have any functions that you know of that would fit down into here? Okay, x to the half. Because that doesn't fit up here. That's not x to a whole number. So x to the half or square root of x. How about some other functions? Natural log x, okay.
The spring formula we had, where it was cosine of dx plus like another constant. So the cosine has multiple terms inside of it.
So you can be like cosine of e to the x plus 1?
Yeah.
Oh yeah, that's a terrible function. Oh yeah, let's never deal with that one. Okay, how about tangent? Where does tangent fit in? Is it here, and the things that we can like, or is it here, or it's in the everything else? It's in the everything else. And you might say, well, what's so bad about tangent versus sine and cosine? Now, think about what happens when you have sines and cosines. When you take the derivatives of sine and cosine, what do you look like? You look like cosines and sines, right? And so you basically look the same. In some sense, the reason that you have nice functions here is that when you look at the derivatives of the functions involved, they more or less look the same or possibly simpler. The simpler could be, for example, if you take derivative of x to the fifth, it becomes something x to the fourth. When you take the derivative of tangent, what do you get? Secant squared, a little bit bigger. Derivative of secant squared, of course, 2 secant squared tangent. And the next derivative, hopeless. Forget it. We're not going to do that in our head. It just grows out of control. Okay, how about sine squared x? Where does sine squared x fit in? Is it up here or down here? It's up here. Now you might say, what? That doesn't seem right, Steve. But why can't it be up here? Oh, there's two people in the back very excited. Okay, so someone said, hey, sine squared is a trig thing. And one of the things about trigonometry is we can rewrite it. And in this case, sine squared, we can rewrite it into two pieces. The half, that's basically like 1, and a half cosine 2x. And that's perfectly fine. And so it could be the case that with a little bit of nudging, you can make it fit into here. But generally speaking, we expect our answers to look like that. Okay, so we're going to walk through a case. So to help illustrate the general idea. So it's going to look like a lot because there's a lot going on here. But here's the takeaway before we get too far down here into this rabbit hole, is we're sort of peeking into the black box. Once we've had our peek and we're satisfied, we're going to close that black box and just be like, okay, and here's what we do. So the work that you see here is not the work that you have to do in general. It's just saying, why do things work the way that they work? So let's go through it. So we're starting with the differential equation. So y double prime minus 3y prime plus 2y equals 4x plus e to the x. So that's our goal. And in particular, we're really after, we could say the general solution, but we're focusing most of our energy on our particular solution. And we're going to find it convenient in our discussion to switch into our notation where we use the capital letter D to represent derivatives. So if I see d times something, that means take a derivative of it. So d times y is y prime. What is d squared times y? Y double prime. So we can translate this left-hand side. Okay, that's d squared minus 3d plus 2, because that's y double prime, 3y prime, 2y. And we say, okay, well, the first step, solve the homogeneous differential equation. You might notice, by the way, I didn't point this out on the previous page. Well, we can point it out really quickly. If you're really good at taking notes, we've talked about non-homogeneous before. We actually swapped the order. So previously we said, oh, find the particular solution, then find the homogeneous solution. And now we're saying, no, find the homogeneous solution first. And today and tomorrow we'll see, it's actually important to find the homogeneous solution first because that helps inform our particular solution. Okay, so we're finding the homogeneous solution first. Well, that's not so bad. You're taking the 4x plus e to the x and setting it equal to 0. So we have 0 equals our differential equation. We can factor d squared minus 3d plus 2 factors. And now when we have into this form, we say, okay, we're basically ready to write down our general solution. Now remember, when we talk about this notation using D, we can switch to our characteristic polynomial very easily. And the way you switch is, wherever you see the D, put an R. So this is R minus 1 times R minus 2 equals 0. So what are the roots? 1 and 2. So our solution, some constant e to the 2x, that's the R equals 2. Some constant e to the x, that's the R equals 1. So here's our homogeneous solution. Okay, no surprise, no surprise. Now we're going to tackle the non-homogeneous part. And here's how we do it. We look at the function 4x plus e to the x. And we say to ourselves, all right, let's find a nice differential equation where that's a solution to the homogeneous version of it. In other words, we want y equals 4x plus e to the x when we plug it into a differential equation to get 0 out. So let's think about our pieces. We have 4x. What can I do to 4x, and thinking in terms of derivatives, to make it 0? Two derivatives, right? So if I take two derivatives of 4x, I get 0 out. So you might notice there's this part right here which says d squared. That stands for take two derivatives. So that d squared would knock the 4x out. Okay, how about e to the x? A differential equation where I plug e to the x in, I get 0 out. What can we do there? Is there any differential equation we can think of? We plug e to the x in, we get 0 out. We can probably make one up. How about this? What's the derivative of e to the x? E to the x. Okay, you know that one. Good. So, y prime is e to the x, and y is e to the x. So what's true about y prime minus y? 0. So y prime minus y is a differential equation which zeroes out e to the x. Well, that's the d minus 1. So we say, okay, the 4x gets zeroed out by the d squared. The e to the x gets zeroed out by d minus 1. Another way to think about it, and it's going to be a good way to think about it going forward, is if I'm thinking about e to the x as a solution to a linear homogeneous differential equation, it came from some value for r. R equals what? Yeah, this comes from r equals 1. So it's like, okay, I need a factor of d minus 1. What about the 4x? Where did that come from? R equals what? What? 0. But notice, if I just have r equals 0, that would just be a constant. How do I get up to x? I have to bump. So I need a double root. So just 0 once would just be a constant. 0 twice gets me up to x. So I can read off the function that says, oh, okay, that tells me what kind of roots I need, which tells me my differential equation. So here we go. Our function y, so when I talk about our desired y, what that means is the y, which satisfies this differential equation, has the following. Well, start by noting 0. That's d squared times d minus 1 times 4x plus e to the x. Well, that's because 4x plus e to the x, we chose this differential equation to zero out 4x plus e to the x. Okay, that's what we did down here. And now, we say to ourselves, aha. Well, we might say, aha. We say, look, there's a 4x plus e to the x right there. And what does this equal? Well, that's the d squared minus 3d plus 2y, which is d minus 1 times d minus 2y. So I'm substituting, since I know 4x plus e to the x equals, I throw it in. Now, we see that our function y, well, it's a solution to this differential equation where we have d squared d minus 1 squared and d minus 2 all times y. Well, in terms of r, that's the r squared, r minus 1 squared, and r minus 2. So we say, hey, I know what solutions look like. So our function that we're after, the function that solves what we want to solve, well, we gather the roots. There's an r equals 2, r equals 1, but then there's a double root for 1. So you have another term where you bumped it up. R equals 0, and again another r equals 0. So anything which solves this differential equation has to have this form. That's what we've come to the conclusion of. But there's two parts here. Now, one part looks very familiar, namely this part, because it's the homogeneous solution which we already knew about. And so we say, okay, that's the part we already knew about. So that means that the other part, this some constant x e to the x plus some constant times x, that's the non-homogeneous solution. And so this is our great aha! We know what our y sub p looks like. So this part right here, this is our y sub p going on the back side. We know what it looks like almost. What's the problem? What don't we know? We don't know those coefficients. So the only thing left for us to do is to say, well, what coefficients make this work? So how do we do that? And we say, all right, well, we know if we plug it into our differential equation, so if we plug this into our differential equation on the left-hand side, we've got to get the right-hand side out. So we say, all right, so let's suppose y has the form that we know it should have. So something times x e to the x, something times x. A, b, and c constants to be determined. So we take the derivative. The derivative of x times e to the x is x plus 1 times e to the x. Derivative of a constant goes away. Derivative of a constant times x is just a constant. Take the second derivative. You'll get that constant a times x plus 2 e to the x, and then the derivative of c goes away. So 4x plus e to the x is equal to y double prime minus 3y prime plus 2y. Well, we know what y double prime is, so we put that in. Minus 3, we plug in what y prime is. Plus 2, we plug in what y is. And so we have this very long expression. But now we start gathering our terms together, like terms together. So let's think about things that we have. We have here x e to the x. Let's gather all our x e to the x's together. How many x e to the x's do we have here? One times a. So there's a of them. How many x e to the x's do we have here? Negative 3a. How many do we have here? 2a. Plus a. Minus 3a plus 2a. Combined together we get 0. So there's no x e to the x's left. That's okay with us. We don't want any. All right, how about e to the x's? Well, how many do we have in there? 2a. How many here? 3a minus, right? How many e to the x's in the last piece? None. So we have a total of 2a minus 3a. How about x's? Do we have anything times an x? Just x. Just at the very end. 2c. How about constants? No constant there. Middle term? Negative 3 times c. Last term? 2 times b. Okay, so we have our form for what this particular solution should look like. We plugged it into our differential equation. We grouped things together. And now we say, okay, in order for this to work, the function 4x plus e to the x has to match this side here. And now we play our great matching game. What should be true about 2a minus 3a? Should equal 1, right? Because I'm comparing coefficients of e to the x. And the coefficient for e to the x on that side is 1. So we better have 2a minus 3a to be 1. Okay, how about the 2c? What should be true there? Should equal 4, because the coefficients have to match. How about this minus 3c plus 2b? 0. Why? Yeah, because the constant over here is plus 0. So if something's missing, we make that equal to 0. So now we have 3 equations and 3 unknowns. But if we can figure out the right choices for a, b, and c for this to work, then we're good. Well, is there a choice for a where 2a minus 3a equals 1? Negative 1. Because this is the same as negative a equals 1. So we say, okay, a equals minus 1. Is there a choice here? Let's go to this one. For c, where 2c equals 4 will work. 2. All right. Is there a choice here for b? What did you say? 3. So we have negative 6, because we know what c is, plus 2 times something equals 0. Yeah, okay, so b should be 3. And now I say, aha, we had the right form, we just didn't know the coefficients. They were undetermined. But now they've been determined. And therefore, we can say that our particular solution will be a, which is minus 1, so minus x e to the x, plus b, so that's plus 3, plus c, which is 2 times x. And there we go. So here's our solution to the non-homogeneous part. That's the idea. Okay, so like I said, this is sort of peering into the black box. Let's open up the hood. Let's see what we get. So let's talk about how it works when we're doing it in practice. So here's the summary. So we have our setting. We have constant coefficient linear homogeneous differential equation. Non-homogeneous. So first step is we find our general form for the homogeneous analog. So in other words, set f of x equals 0, and what should our complementary solution look like? Now the second step says, okay, find the general form for solutions to a constant coefficient linear homogeneous equation where f of x is a solution. So let's just remind ourselves of a couple of things. When we talk about solutions to constant coefficient linear homogeneous ordinary differential equations, they look like that. So in other words, f of x has to be some combination of things that look like this. Now they don't have to have the cosines and sines. They don't have to have the exponentials. They don't have the powers of x's. But they do have to be some combination of those individual things. Now when we talk about solutions, keep in mind that if you see a cosine, there has to be a sine pair. And vice versa. If there's a sine, there has to be a cosine pair. And also, if you have a power of x, a higher power of x, you have to have all the powers of x going down. So, let's test ourselves. What's the general form? Suppose f of x, our little f of x, was e to the 3x. Okay. What's the general form look like? I know, very big question.
C e to the 3x?
Yes, some constant, e to the 3x. That's the answer. Okay, all right. Let's try a little bit more interesting. How about e to the minus x sine of x? What would that look like? The general solution. C, e to the negative x, sine of x. Anything else? So d, e to the negative x, cosine of x. Now, whatever the function is, that's got to be part of your solution. So if I see e to the 3x, okay, part of my solution looks like e to the 3x. If I see e to the negative x sine x, okay, that's part of my solution. If I see a sine, I have to have a cosine pair. If I see a cosine, I have to have a sine pair. All right, you ready for more of a challenge? Somebody said yes, so we're going to go there. All right, suppose f of x had been 17x squared sine of 2x. All right, then what would our general solution look like if this is a solution to our homogeneous differential equation? What would a general solution have to include? I'll ask you a quick question. Does the 17 make a difference in our answer? No, it doesn't. So you can ignore the 17. That's a red herring. Okay, so what do we have to include? We have to include this x squared sine 2x. That has to be there. So whatever the function is, that has to be part of your answer. So we'll start with A. Well, what else do we need to have? The cosine pair. What else do we have to have? Because notice we have x squared. So what do we need to do? We have to have an x. X sine of 2x. What else? D.E.s cosine 2x. What else? Yeah, got to keep working your way down. E sine of 2x. What else? Some f cosine 2x. So if our function had 17x squared sine 2x, we would say, okay, our general form has all these pieces in it. Wow, so many pieces. So many opportunities for us to play alphabet soup. All right, there's a question.
So k has to be a whole number, but does it have to be positive?
K has to be a positive whole number, yeah. So we can't have x to like the negative 2. We can't have x to the half. So when we talk about k, we're talking about that exponent x to the k. It has to be a positive whole number or 0. We'll include 0 as positive.
That would be because k is that bumping.
Yeah, k is like the bumping. So we start at 1, which is like x to 0, and then we bump. And we always bump up by 1. All right, are you comfortable? If I wrote something down, you could fill it in? Yes? So if I had said one more, just for fun, right? If I had x cubed e to the square root of 2 times x, is this valid, by the way? Yeah, this square root of 2 is fine. You can have weird numbers here. You just can't have weird numbers in that power of x. Okay, so what do we need? Okay, the function itself. And then? Yep, got to work our way down. X squared. And then? Cx e to the square root of 2x. And then? D. Now, I should say that so far we've just done individual pieces. What if we had done multiple pieces? What if we had, say, f of x is x squared plus sine of x? How do we handle that? Okay, someone said ax squared plus bx plus c plus d sine of x e cosine of x. And the point here is that you say, look, if I have plus, I just do the one part gets a part of it. So the x squared has that contribution, ax squared plus bx plus c. And then the other part, which is the sine, That's the contribution going to the rest of it. So in other words, when you have pieces being added together, just do them each individually and put it all together. And there you go. Okay, so that's the first sentence here. But then there's this second sentence, and it's italicized, as if to say, this is an important sentence. This is something you should pay attention to. We should even color it. Wow! Now it's a colored sentence. Very important, this sentence, whatever it is. Well, what is it? It says, if you have anything that overlaps with what you found in part 1. So part 1, remember, that's this complementary solution. If there's anything that overlaps in part 1, whatever the overlap is, you got to bump it up. Bump it up, bump it up. You got to get rid of the overlap. Because overlap is useless. Because when you have anything that overlaps, if you plug it into the differential equation, it just goes away, goes to 0. It can't help you. Now you might say, well, how did that show up before? If you walk through the previous problem, you'll notice that we had 1 was a root of the original function, but it also was part of our non-homogeneous thing, which caused it to bump up. So instead of being e to the x, it became x e to the x. So that's where that was showing up in the previous problem. It helps to bump it up to make it work. Okay, so we now have the form. We say, after step 2, we know what our answer looks like up to, we don't know those coefficients. They're undetermined. So that's what step 3 says. Let's find those coefficients. So we feed the answer from step 2, we feed that into our differential equation, and then we look at the coefficients and say, okay, how do we choose our constants so that our coefficients will match on both sides? And that helps us to finally find our particular solution. Okay, so that's the idea. Let's try it. Find the general form for solutions of y double prime minus 4y equals e to the 2x. All right, so what's the first thing we need to do here? So first thing, very conveniently for us, we have it on the screen here. Well, we would find the y double prime minus 4y equals 0. If we convert this to the characteristic polynomial, what is the characteristic polynomial? R squared minus 4r. What are the roots? Oh, sorry, not r squared minus 4r, r squared minus 4. Because that. So what are the roots? Plus or minus 2. So, what is our complementary form look like? Some constant, e to the 2x,
plus dx, e to the 2x.
Some other constant, e to the minus 2x. Okay, so that's this first step. That's a step which hopefully you feel good about, because we've done that before. Step 2, we say, hey, e to the 2x. So, our first guess, since we have, this is our f of x equals e to the 2x. Well, what should we say that our solution should look like? Don't be clever yet, just ignore step 1. We see e to the 2x, what should we have here as our form? What should it look like? Yeah, a e to the 2x. And then we say, okay, now let's compare. We compare and we say, is there any overlap? Yeah, they both have e to the 2x's. You can't fix the overlap here. It has to be in the particular solution. So we say, oh, there's overlap. And so we're going to do some bump. So what will our new particular solution look like? A x, e to the 2x. We bumped it up. So now is there overlap? No. So we bumped it up so there's no more overlap. So that's good. So that's going to be the form that our particular solution has. The only thing we don't know is a. That's all right, because that's the next step. Okay, so here we go into step 3. So, what do we do? Well, we now are going to plug this function into our differential equation. So we have that e to the 2x. Well, that's y double prime minus 4y. That's ax e to the 2x double prime minus 4 ax e to the 2x. Okay, and now perhaps the challenging part of this problem. What's the second derivative of x times e to the 2x? How about we start with the first derivative? First derivative of x e to the 2x? Sorry, what?
E to the 2x plus 2x
E to the 2x plus 2x e to the 2x. Okay, product rule. Derivative of the first is 1, then times the second function, plus the original function x, derivative of e to 2x, would bring a 2 down. 2x e to the 2x. All right, y double prime. Okay, derivative of e to the 2x? 2e to the 2x. Derivative of 2x e to the 2x. Well, we'll have 2e to the 2x, taking derivative of x, and then 4x e to the 2x. When you take derivative of e to 2x, another 2 comes down. So if you put that all together, you'll get 4e to the 2x plus 4x e to the 2x. Okay, so that's the second derivative there. So that's equal, don't forget the a. So we have a times all of that, 4e to the 2x plus 4x e to the 2x minus 4, well, and then that. Okay, now we gather. Well, we see x e to the 2x. Let's gather all those. How many x e to the 2x do we have from the first term? 4a. How many from the second? Negative 4a. We put that together, we get 0. And I'm going to go ahead and write that out. You get 0x e to the 2x. And is that good that we ended up with the 0 there? Yeah, because there's none of them over there. If we had something there, we might get worried. But we're not worried. Okay, how many e to the 2x's do we have? 4a. So plus 4a e to the 2x. All right, so this we don't need to worry about because 0 takes 0 is 0. In order for these to match, what needs to be true? Yeah, 4a needs to be 1. So this is, we set the coefficients equal to each other and have a system of equations. Well, it's a very small system of equations. So what can we say about a? A is 1/4. So we can put that a back up into here and say that our particular solution is really 1/4 x e to the 2x. So now we have our particular solution. Are we done? No, but we're really close. What's the last thing for us to do? Well, what is it we're looking for? Well, I'm asking because, we need to find it. Oh, wait, no. The general form. You mean, yeah, you want the function y. Okay, so how do we find the general form? Yeah, we combine the two together. Our particular solution and our complementary solution. It doesn't matter which one goes first. So we can say, look, our solution for y, 1/4 x e to the 2x plus some constant e to the 2x plus some other constant e to the minus 2x. And that's it. That's it. All right. Well, you ready for another one? Mwahahaha. Oh, ha, 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 ha. All right. We probably won't be able to finish this one, but at least we can start it. Solve the initial value differential equation y double prime minus 3y prime plus 2y equals 3 e to the negative x minus 10 cosine 3x. Now, you'll notice there's something missing on this initial value problem. What's missing on this initial value problem? Yeah, you're right. Good. Wow, you guys are nailing that. Okay, so let's just make some up. We probably, like I said, I don't think we'll reach that point. So what do you want y of 0 to be? What do you want y prime of 0 to be?
Y of 0 is 4.
Y of 0 is 4. Okay, someone is like, aha, I have an idea. Okay, y prime is 0? Negative 2. Yeah. Y primes, yeah, initial values can be negative. Okay, so we run the process. So we'll hopefully run it a little bit faster. So step 1, what's the first thing we do? Yeah, do the homogeneous part. Y double prime minus 3y prime plus 2y equals 0. Turn that into r's. What does it become? R squared minus 3r plus 2 equals 0. Okay, does that factor? He asks us, he writes it down like it does factor. R minus 1, R minus 2. So what are the roots for R? 1 and 2. So our complementary solution looks like C1 e to the x and C2 e to the 2x. Okay, so that's not new. This is stuff we've already done. Now the new part. Okay, so 2. Our function f of x, I'll write down again for reference, is 3 e to the minus x minus 10 cosine of 3x. Okay, so that's our function for f of x. So what's the form that our particular solution should take? Okay, so that e to the minus x, what would we have? Something times e to the minus x. Okay, how about this cosine? What do we need? Plus b. Cosine 3x, anything else? Yeah, cosines and sines come in pairs. Okay, anything else we need to add to this? Not yet, right? In terms of the function, that's what our particular solution should look like. Now, do we need to bump? Let's compare. Is there any overlap? Yay, there's no overlap. Woohoo! Victory for us. Okay, so we now know our particular solution looks like that, other than we don't know A, B, C. So as soon as we learn our ABCs, we'll be ready to go. All right. Well, how do we do that? Well, we go to step 3. So we're going to have our 3 e to the minus x minus 10 cosine of 3x. Well, again, that's equal to y double prime minus 3y prime plus 2y. In fact, just to emphasize, we're doing our particular solution. So as I'm plugging in the particular y sub p, plugging that into the differential equation. We say, look, this has to hold. You just have to figure out the right choices. Okay, so that says you take a e to the minus x plus b cosine 3x plus c sine 3x double prime minus 3 a e to the minus x plus b cosine 3x plus c sine of 3x prime plus 2 a e to the negative x plus b cosine 3x plus c sine of 3x. All right. Well, whew, other than there's a lot to write down, nothing too scary yet. Second derivative of a e to negative x, what would that be? Ah, that's nice, a e to negative x. Second derivative of cosine of 3x. Okay, the negative came from cosine goes to negative sine goes to negative cosine. Where did the 9 come from? Yeah, every time you take a derivative, the 3 has to come out. So, minus 9b cosine 3x. Two derivatives of sine of 3x. What would we have? Minus 9c sine of 3x. Okay. Minus 3 times one derivative of a e to negative x. What will we have? Negative a e to negative x. One derivative of cosine 3x? Minus 3b sine of 3x. 1 derivative of sine of 3x.
Plus 3c cosine 3x.
3c cosine 3x. Plus 2, and now we just have to copy. Good. Okay. Any questions on what we've done? Again, there's a lot of, if you just look at this and like, you might feel overwhelmed by the text, but the idea is not so bad. It's we took our particular solution, we say we know our particular solution looks like this, and we threw it in, and then we're just cleaning up. What's our next thing to do? Yeah, we're going to put terms together. Okay, so for example, we have e to negative x's. So let's put them all together. How many e to negative x's do we have from the first term? Well, we have a. From the second one? 3a. From the last one? 2a. And that's our e to negative x's. All right, what else do we have to combine? How about the cosines? So we have cosine 3x's. So how many do we have from the first piece? Minus 9b. From the second piece? Minus 9c. From the last piece? Plus b? 2b? Or is it not 2b? No, it's 2b. It's 2b. All right. I know. This isn't an English class. No jokes about Hamlet here. Okay. The signs. We see the signs. And we're going to combine them together. So what do we have for the sine function? Minus 9c and? From plus 9b. From the last one? Plus 2c. Sine. Okay, so now we clean this up. A plus 3a plus 2a is also known as 6a. So 6a is the coefficient of e to the negative x. What do we want the coefficient of e to the negative x to be? 3. So 6a better be 3. All right, minus 9b, minus 9c plus 2b. We can write that as minus 7b minus 9c. That's the coefficient of cosine 3x. What do we want the coefficient of cosine 3x to be? Negative 10. Okay, minus 9c plus 9b plus 2c. Well, that's minus 7c plus 9b. That's the coefficient for sine of 3x, which the coefficient for sine of 3x should be 0. Because if it's not there, it better be 0. So now we have 3 equations, 3 unknowns. All right. Well, I claim we can solve one of these pretty quick. Which one? Oh, yeah, A. Oh, sure, yeah. Don't you know? Okay, what is A? A is a half. We've made progress. Okay, how do we solve for B and C? 2 equations, 2 unknowns. We're going to be doing a lot of this stuff in the near future. Okay, you can do substitution. That works great. Here's another thing you can do. This is called getting cancellation. So let's multiply the first equation by 9 and the second equation by 7. Then you'd have minus 63b plus 63b, which means there's no more b's. Apocalyptic. Minus 81c minus 49c. What does that make? Minus 130c. Minus 90 plus 0. Minus 90. So what is C? 9 over 13. Now that you know C, B is not far behind. So let's quickly solve for B. So we have 9 times B minus 7 times 9 over 13 equals 0. 9 times b is the same as 7 times 9 over 13, because I just moved that across. So what can we say about b? 7 over 13. So our particular solution, well, is 1/2 e to the negative x plus 7/13 cosine 2x, because that's b is 7/13, and 9/13 sine of 3x. So that's the particular solution. So we have the particular solution. We have the homogeneous solution. So what can we do now? We can combine and get the general solution. And are we done after that? No. What would we have to do then? Use initial conditions. But clearly we're over time. So we'll just stop here and be like, wow. And that's just one problem.